Okay, so we're going to look at do a quick review of forces. The key to remember for forces is Newton's second law. All right, at least for the calculations. Newton's first law says an object in motion stays in motion, an object at rest stays at rest unless acted on by an unbalanced force or an outside net force. So in other words, to accelerate something or to change its velocity, you have to apply unbalanced forces. Another way of saying it is if an object is stationary or moving at constant velocity, the net force on it must be zero, or all the forces acting on it must be zero. So Newton's second law, sigma F net force equals ma. Forces are balanced, and that means that net force equals zero, the acceleration is zero. For example, if I have the force of gravity acting down, that must mean that the normal force is balanced acting straight up. The way that would look mathematically is that the net force is equal to zero. So force of gravity, which is down, is negative, plus force normal, which is up, equals zero. And if I were to solve this equation for the force normal, then I would get force normal equals gravity, which tells us that these two forces are balanced. What about for an object acting with sideways forces? For instance, a car driving down the street, cruise control set, you're going at a constant velocity. So we already know about force normal, force gravity, but if it's moving at constant velocity, then that means that the net force equals zero. Solve that for the applied force. It must be equal to the resistive forces, or the force of friction. On the other side, if forces are unbalanced, net force is not equal to zero, the acceleration is not equal to zero. That must mean that one force is bigger than any other force acting on it. So mathematically, that would be sigma F, instead of being equal to zero, is equal to ma. So here I look at the net forces, Fa. If I call this the positive direction, positive x, and that's the negative direction, then Fa would be positive, force of friction would be negative, equals ma. Solve that for the force applied. I'd have force applied is equal to ma plus the force of friction. So that's how it looks mathematically. That's what it looks on a free body diagram. What about an elevator? What if an elevator was accelerating upward? If an elevator is accelerating upward, then that means that there is a positive net force upward. Mathematically, or so that this is what it would look like on a free body diagram. This would have to be bigger than Fg. Mathematically, net force equals ma. Force normal minus Fg equals ma. So in this case, the normal force is equal to ma, your mass times the acceleration upward, plus the force of gravity. So this is mathematically explains why you feel heavier when an elevator is accelerating upward. Of course, as soon as the elevator goes to constant velocity, then it would look like this situation. Constant velocity means no acceleration. So force normal is equal to force gravity. Keys to remember: constant velocity, unchanging velocity. Velocity can be zero, or it can be, I don't know, anything, 20 meters per second. As long as it's not changing, then the forces must be balanced. If you have a changing velocity, any change in velocity, whether that's speed or direction, can only happen if the forces are unbalanced. So that's a quick review. Let's look at the free response on version A. A ball that was thrown upward and is in the air, ignore air resistance. So, it's in the air. There's only one force acting on it, force of gravity. That's it. A car going down a highway, cruise control set at 55 miles an hour. Well, we know we have a force of gravity. We have a normal force that's balancing out that force of gravity. We have resistive forces, because this is talking about the resistive forces. Force, I'll call that R, resistive forces, which is drag force and friction. If this was all that was happening, then there'd be a net force backwards, and the car would be slowing down. So in order to maintain that speed, the car has to work. The engine has to put some work into it, has to apply some power. But with constant velocity, these two forces are the same. A box sliding down a ramp at constant velocity. Alright, so here's our ramp. Box sliding down. This is the one that gets a little tricky. Gravity is always straight down. Fg. Normal force is perpendicular to the surface. Force normal. Now, if these were the only two forces acting, the box would be accelerating down the ramp because we would have these two components of the force of gravity acting. Fgy would be balanced out by force normal, and this would be causing the box to accelerate. So in order to have a constant velocity, you must have another force that is opposite the Fgx, which is force of friction. So these two forces must balance. And quick reminder, if you have a ramp, you're going to set the coordinate system so that it is the x direction is parallel to the ramp. That just makes the problem easier to solve. Alright, now this one there's some confusion on. A lot of people want to put this on a ramp, but there's no ramp, it's a car, and you are pushing down at an angle. Car is moving with constant velocity, so all the forces must balance. So force of gravity, straight down. You are pushing down at an angle, so we break that force down into the component parts, Fx and Fy. So I have two downward forces. That must mean that the normal force is balancing out these two forces. Fn must be equal to Fy and Fg. There's also a horizontal component of the force, Fx. That must be balanced out by a force of friction. So that's a pretty complicated one. That's as hard as it gets in this class. So that's what it looks like. Okay. For the other problems, 28 kilogram box being dragged horizontally. There's your solution. Constant velocity tells us that all the forces must be balanced. So the force of gravity is equal to the normal force. The force of the person dragging it, or the applied force, must be equal to the force of friction. So I analyze everything. First I do the y direction here to find out what the force normal is. The reason I start with the y direction is because I realize when I'm using force of friction, I'm going to be substituting mu force normal, since force of friction is equal to mu force normal. When I do the x direction, all the forces acting in the x direction must balance, so the force of friction is equal to the force applied. I substitute mu force normal, solve for mu, get a mu of 0.036. A little complicated, but certainly doable. It all starts with Newton's second law, looking at the net forces, looking at the free body diagram, understanding if it's accelerating or not. If it's not, then you can set those forces equal to each other. Flip this over. Box sliding down a ramp. Two forces acting. Force of gravity straight down, force normal straight up. We're going to set our coordinate system so that y is perpendicular and x is parallel to the ramp. So the angle of the ramp is reflected by the angle between Fgy and Fg. Fg, by the way, is broken into two component parts. Fgy must equal Fn because the box is not accelerating in the y direction. The box is accelerating down the ramp. So I look at the forces in the x direction. The net force in the x direction is Fgx. That causes the mass to accelerate. So we get to the solution here. Now part C says we are going to add friction. So here, I peel this away. There must be a force of friction acting up the ramp. We don't know if these are balanced or not, but we are going to analyze all the forces acting in the y direction. It's force normal minus FGY. And the reason I'm doing that is because I need to find out the normal force. Normal force is equal to FGY, 216.5. Because I'm going to need the force normal when I go to calculate the force of friction. So all the forces acting in the x direction. There are now two forces acting in the x direction. FGX minus force of friction, causing the mass to accelerate. So I solve for A, or the acceleration in the x direction. FGX minus force of friction divided by m. And then I'm substituting. Instead of FGX, it's mg sine theta. Instead of force of friction, it's mu force normal, which earlier I figured out mu force normal is equal to mg cos theta. The masses cancel out, and I have an acceleration that is equal to g sine theta minus mu cosine theta. Now this is a result that is only valid for this one situation. You can't always use this acceleration for various problems. So the acceleration is 2.56, which is less than the acceleration without friction, which should make sense because we have added a force that's working to retard the motion. So you would expect a smaller acceleration. And if you were to get a negative acceleration, that would mean that the box was slowing down. And eventually you would have, it would go to a zero velocity, in which case it would become static friction and the acceleration would be zero. All right, so here's a solution to the last problem. Give the problems that I've posted online a try. Well, don't just try them, solve them. Give them to me on Tuesday. You'll get some extra credit towards your final grades. Some of you could really use that. It'll also be very good practice for the midterm. All right, that's it for this screencast. Take care. You know, I'm realizing I almost always say take care at the end of the screencast. I'd like to say something a little more interesting, more dynamic, but also caring. So help me come up with an effective closure to my screencast. Maybe I'll throw a few extra points your way. Something like, this is C433 signing out, or I don't know. Help me come up with something creative. Have fun. Take care.